Hi, today we're going to be talking about reactions in aqueous solutions, chapter 11.3. Okay, this picture is showing you soda straws or stalactites, which you find in limestone caves. They're coming down from the ceiling. They're very thin-walled hollow tubes, and it basically results from chemical reactions involving water, and we're going to talk about those later in this presentation. Okay, we're going to talk about something called the net ionic equation, okay? And it's basically shows only those species that actually change in a chemical reaction. We saw in the last section that double replacement reactions often occur with solutions, and for them to occur, some of the things that are dissolved all of a sudden become a precipitate on the product side. So it's just going to show those things that make products that are no longer soluble, for instance. Now, why are we worried about things that happen in water? Well, we know that most of the Earth's surface is covered with water, and most of you are made out of water. So this is why it's so important to know a little bit about what kind of reactions occur in water or aqueous solutions. And we'll talk later on a lot more about aqueous solutions or solutions in general. All right, so we have two compounds that are dissolved in water. We have silver nitrate in one beaker, and we have sodium chloride in another beaker. If we mix these, or even as the picture shows, we might have one in a pipette or a burette, and we add it to the other solution, we will end up getting precipitate. In this case, according to the equation, silver chloride is not soluble, so therefore it will precipitate out. Okay, so these are two solutions. When you mix them together, you end up getting silver chloride. Notice sodium nitrite is aqueous. Okay, so this means sodium and nitrate ions are still swimming around in the beaker. Sodium was swimming around and nitrate was swimming around in the other two beakers, so these have not changed. The only things that have changed is the silver and the chloride. So they are going to end up in our net ionic equation. Okay, so it's not showing us the separation of the ions. So that's what we're going to do with our net ionic equation. So we know that sodium and chloride separate into these two ions in aqueous solutions, and they're floating around in solution. And we also know the silver and nitrate do the same thing. So what we can do is we get a complete ionic equation. That's where we break everything down. We have the silver ion, nitrate ion, sodium ion, and chloride ion. Notice they all are aqueous, means they're in solution. Then on the other side, this is a solid, so it's not in solution. So notice the two ions are together in the ionic compound. Sodium and nitrate are not. So if we look, sodium and nitrate, they're on both sides. That's going to be important. Okay, so we call these spectator ions. Okay, we call these spectator ions, the ones that are seen on both sides. Okay, so what did we do? It's like you're at a ball game. These are the people in the stands. They're not playing the game. The ones playing the game are silver and chlorine. Okay, silver chloride is formed. So these guys are spectators. I don't know why my pen color keeps on changing on me. So spectators are the same on both sides. They don't participate in the reaction. Okay, so they're called spectator ions. They are formed, they are on both sides of the reactions. So when we rewrite the equation, leaving out the spectator ions, that's when you end up getting the net ionic equation. So that means we're going to rewrite it with Ag plus, Cl minus, and AgCl. Okay? So we're going to write it with Ag plus, Cl minus, and AgCl. Okay? So there it is. That is the net ionic equation. It only shows those things that directly participate in the reaction. So in writing balanced net ionic equations, you must also make sure that the ionic charge is balanced. Okay, so we have a +1 and a -1. Great, it's 0. And we know it's going to be balanced in a compound. So everybody's happy. If this was AgCl2, for instance, we would have to have a 2 coefficient there. All right, so let's go through this skeleton equation and then break it down. Okay, so looks like a single replacement reaction. Lead is replacing silver. Okay, and then we're getting silver solid. But what is aqueous in both cases? Okay, so let's take it apart. Okay, so nitrate is aqueous in both cases because it says aqueous. Oops, it says aqueous. So we know we have NO3 minus and we have NO3 minus again. Okay, so what do we have left? We have the lead, the silver ion, silver solid, and lead 2 plus. Okay. So is it balanced? Okay, well, we've got 1 there, we've got 2 plus there, all right? So to balance it, we must need 2 Ags, right? And actually, if we balanced up here, it would make sense because we've got 2 nitrates, okay? So we could balance before, or we could just look at the charges and say, okay, this is 2 plus, so we need 2 plus there. If we do that, that becomes 2 and that becomes 2. The leads are okay. All right, so what we have to do is we have to basically then take this here, the 2Ag, because we have to have 2 plus. Okay? It's one way of looking at it. You could also have balanced the complete ionic equation, or the complete balanced, just balance the equation before you separate it, and it would work out also. Okay, so net ionic equation only shows those things that are involved in the reaction. And it's balanced with respect to both mass and charge. So usually the two things that are going to have net ionic equations are single and or double replacement reactions. All right, so let's have some practice. All right, so we have iron chloride, iron 3 chloride, potassium hydroxide, and a precipitate of iron 3 hydroxide is formed. So we want to identify the spectator ions and write a balanced net ionic equation. So write the complete ionic equation, get rid of your spectator ions, which are seen on both sides of the reaction, reactants and products, and then balance the equation with respect to both mass and charge. So we have iron 3 chloride, we have potassium hydroxide, we have iron hydroxide form, and that leaves us with potassium ions and chloride ions. All right, where did we get, let's break this apart first because I think it's a little confusing the way they just did that to you. I would do this, actually, I would write it this way first. I would write Fe Cl3 aqueous plus potassium hydroxide produces iron 3 hydroxide. I'm going to write this aqueous plus KCl. Aqueous. And I'm going to balance it like I normally would. Okay, so I have iron, chlorine. I need 3 here because the chlorine needs it. That means I'm going to need 3 Ks, 3 OHs, 3 OHs. Everybody's happy. Now I'm going to break it apart. So I'm going to have the Fe3 plus, I'm going to write it, 3 Cl minus, okay, 3 Ks, 3 OHs. So all I'm doing is, these are all aqueous, so I can write them in separate ions. This is a solid, so I don't separate that one. The Ks are aqueous again, and the chlorines are aqueous again. Okay? So I think it's important to see this first. All right. Now, we're ready to go to the next step. We're going to cross out things that we see on both sides. This is the chlorines and the potassiums. And we ended up with the iron 3 and the OHs and the iron 3 OH, the iron 3 hydroxide. Okay? And we'll rewrite that. And that's going to be our balanced net ionic equation. Check charges. We got a 3 plus, 3 minus. This is a compound. It's fine. Okay? So notice by balancing it before, we only have to check to make sure the charges are fine at the end. Okay, what is the difference between complete ionic equations and net ionic equations? I'm not going to ask you this on play pause it. Think about it for a second. Okay, all the ions are shown in complete. Only the ones that are directly participating in the reaction are shown in a net ionic equation. No spectator ions. All right, so now how can we know if we have precipitate, which allows us to say that we have a double replacement reaction? Fortunately, we've got some rules. Okay, there's also tables available, but the rules will help us the most if you look at what the rules state. Okay, some combinations of solutions make precipitates while others do not. And it depends on the solubility of the new compounds if a precipitate will form. So we need a solubility table. We need to know if the new compound is soluble or not. So technically, when we mix two solutions, if they don't form a gas or a precipitate or water, we don't technically call them a double replacement reaction. We can balance them out if we want to, but there's really no big changes that are occurring. So it's not really a reaction then. Okay, so we're going to look at some general rules. This table is something you should take a screenshot of and know what it is. I'm going to actually read this to you because it's so important. All right. Any salt that contains a group 1 or alkali metal or ammonia will be soluble. There are a few exceptions with lithium, but very rare. Okay, so in general, if it's an alkali metal, you can assume it's soluble. If it's one of those lithium compounds, they're going to tell you that it's insoluble. Okay, nitrates, okay, and chlorate salts are always soluble. Nitrate salts are always soluble. Chlorate salts, there's very few exceptions. Okay, so nitrate salts, if you see something like silver nitrate, it's soluble. Okay, sulfate salts are generally soluble, but they do have specific exceptions. So you need to know these. These following sulfates are not soluble: lead sulfates, silver sulfate, mercury sulfate, barium sulfate, strontium, and calcium. So if we look here, if we look at this chart, notice that the last 3 are in group 2. So they're the bottom parts of group 2. So if you look that way, right here. Okay, so what are we missing? We're missing magnesium and beryllium, which would be soluble, but these 3 I'm sorry, yeah, these three are not soluble, and these metals here are not soluble. Chlorides, salts in general, are soluble except for silver and mercury and lead. Carbonates, phosphates, chromates, sulfides, and hydroxides are usually insoluble, but of course we said alkali metals and ammonia are. So this means if it has this, it's soluble. If it has nitrate, it's soluble. These are some that have exceptions, okay? But these here are always insoluble. So you can, if you make a carbonate, if you make a phosphate, chromate, sulfide, or hydroxide, you're usually going to have a precipitate. All right, so let's look at this equation. We have sodium carbonate and barium nitrate, okay? And if we look at what we started with, here is all our ions. All right, we have 2 sodiums, we have 1 carbonate, 1 barium, and 2 nitrates to start with. Okay, so the idea is we're going to switch partners. So we're going to have sodium nitrate. Okay, sodium nitrate we know is soluble. That leaves us with barium carbonate. Okay, so if we go back, okay, carbonates. Okay, the only carbonates that are soluble are alkali metals and ammonia. Barium is not that, so barium carbonate will be insoluble. It will be a precipitate. Okay, so those are the 2 possibilities. As I said, sodium nitrate is soluble, barium carbonate is not. All right, so that's a summary of what I said. All right, so now we have, yes, we will get a precipitate. It will look like what's in the test tube. What's our spectator ions? Okay, we said the sodium and nitrate are spectator ions, so what do we end up with? Barium and carbonate. Okay, we've got a 2 plus and a 2 minus. They cancel out. That's our net ionic equation. Okay, you might wonder then, how did those soda straws or stalactites form? Calcium carbonate, we know, is not really soluble in water. So it's slightly soluble. So as it drips down, it's carried along with the water, and then it basically, as the water goes away, the calcium carbonate stays behind. All right, and so it forms that as the water washes down or drips from the ceiling. All right, let's walk through this problem together. So we have potassium carbonate and aqueous strontium nitrate. Potassium carbonate, group 1 metal, so that we know that's, they tell us it's aqueous, so we know it's dissolved. And strontium nitrate, it's a nitrate, we know it's going to be soluble. It's also a nitrate. All nitrates are soluble, so that makes sense. Okay, so now we're going to switch partners. Okay, if we switch partners, before we even think about writing it, we'd end up with potassium nitrate, soluble, it has a nitrate. Strontium carbonate. Carbonates are usually insoluble unless they're group 1 metals. That's going to be a precipitate, so there probably will be a reaction. Okay, so let's go through that. We did that in our head. Now we're going to see it. We're going to write out the reactants. So everything is soluble to start out with. So we have potassium carbonate, 2 minus, so we need 2 carbons. All right, I'm going to do something a little bit different because I don't think it's a good idea. Make your compounds first. Okay, so you have K2CO3. This is minus 2, this is plus 1. You need 2 when you cross. Plus strontium, which is 2 plus, nitrate, which is 1 minus. So you're going to need 2 of those. Okay, these are aqueous. So that means we can split everything apart. So 2 potassiums, 1 carbonate, 1 strontium, and 2 nitrates. Okay, so I think it's always a good idea to write the formulas out like this and then separate them. This doesn't make sense to go to this step right away. Okay, so then we switch partners, okay, and we get potassium nitrate and strontium carbonate. This is soluble. This is not soluble. Okay. All right. Then you eliminate the spectator ions. Okay. So the only things that we don't see on both sides are the carbonate and strontium. So the charges are the same. So that's our balanced equation. Okay, I'm going to ask this question on play posit. So read it. I'll rewrite it for you, and we'll be back in a second. Those are the ones that stay in solution. All right, in summary, definitions. Know these definitions. They will be on a test. Okay, the big idea, reactions. Net ionic equations show only those particles involved in the reaction. That's it. All right, have a good one.